and gentlemen. So I will give you information regarding the targeting patient safety as we perform by using the QBD approach. So I will start with, with the product definition, which is quite current at the start of the project. But then I will describe how we perform the quality by design approach with some examples based on IVIG process development. And I finished with making some conclusions. So at first, for the project, we have to define what product we want to target. So for IVIG, it's quite common to talk about tolerance with decrease or removal of some impurities like IgA, procoagulant factors, and hemagglutinins. The other topic would be related to liquid form with the removal of proteolytic activities and some unstable proteins. For biological safety, we decided to introduce solvent and detergent treatment and 20 nanometers filtration that leads to a decrease in high molecular weight proteins. And for efficacy, we have to maintain the product profile, mainly related to IgG subclasses, and to maintain also the repertoire of biological activities. So this is quite current for IVIG. Then we adopt a quality by design approach to perform this process and product development. The first step was to define the product design and to identify clearly the quality target profile product. That means that we clearly identify the main characteristic of the product we want to obtain. The second step is related to product risk analysis that leads to the identification of the critical quality attributes of the product. That means for each of these attributes, we have one or more analytical method to identify and quantify the product characteristic. The next steps are related to process risk analysis and process risk mitigation. The first step was to identify the critical steps of the process, and the second one, to mitigate the risk by identifying through robustness studies and process verification what are the critical process parameters and their limits. And the last steps is related to control strategy. So identification, which is a combination of process and product controls. That means we have clear justification of each of these specifications. So at the first, I would like to exemplify that the product design is related to process design. Taking as an example the major quality target profile items. For example, the first one is related to the reduction of potential adventitious and non-adventitious agents, which is obtained through the two specific biological safety steps. For another item, removal of activated coagulation factors, we have a specific step dedicated to this one, which is caprylic acid fractionation. Another one is related to removal of depletion of hemagglutinins with a specific affinity chromatography we have patented at first and developed for this purpose. And the other one is related to removal of aggregate proteins with a specific filtration step in the process. And last major item is related to removal of IgA, which is obtained through the anion exchange chromatography. So you can see there that for each item, we have a dedicated or two dedicated purification steps. The conclusion of the product risk analysis was for IVIG the definition of the 19 critical quality attributes. So the objective was to manage the performance of the process to clearly obtain these product characteristics. through process risk analysis. The first was based on process knowledge and through identification of the step contribution to each quality of the product. We can identify it's a major or minor contribution, and by this way to define what are the critical steps of the process and to focus our development on these steps. The conclusion of this analysis was to draw the mitigation plan with specific studies, which were mainly robustness studies for the purification process steps, also for chromatography step, the gel aging studies, then specific validation studies, for example, for viral validation, for process validation, and the last item was the stability study to document the stability of the final products. Here I can give an example of the technical information we can recover for process robustness study. I choose the example of the anion exchange chromatography, which is contributing to the removal of IgA proteins. And through the robustness study, we identified that 3 parameters were acting in the final level of IgA, and by this way to define the normal operating range, where there was clearly the same product, and the proven acceptable range, so they are the limits that help us to obtain the compliant product. So at the end of this type of study, we have a clear identification of the impact of the process parameters, operating conditions, on the final product characteristics. It is very important to prove that we clearly understand our process and our product, and in this field, we are able also to manage the final product quality through the routine manufacturing of the product. So, on the same way, we can have a global overview of the process with the different critical process step, with the identification of the critical process parameters for each step, and the definition of the limits we can cover during routine manufacturing. The last step for robustness and process study was verification at full scale. In this condition, we introduced the industrial constraints and define the strategy for validation batches. Generally, we work at the target value, but in some cases, we have justification to cover the whole range. For example, when the parameter is not fully scalable, we have to verify on the full range that the results are confirmed at full scale. And in some cases, we want to confirm the worst case situation or to smoothly extend the proven acceptable range related to industrial constraints. The validation batches were performed taking into account this justified strategy and proved that the process was also controlled at full scale. So based on this robustness and full-scale validation, we can identify that for all the critical steps, the risk moved from high or moderate to acceptable level. So we have very confidence and some proofs to go through the routine manufacturing condition. For the control strategy, we have generally positive outcomes, but also some limitations. So as an example of the positive outcome, I choose the elimination of solvent and detergent content in the final product, which was obtained through the 2 identified steps with robust and based on robustness studies and full-scale validation. We can prove that the control of the final product can be obtained through the control of the operating process parameters. For this reason, the validation of these 2 solvent and detergent clearance steps justify the removal of solvent and detergent testing from the routine testing as the product is conducted within the operating condition range we have primarily defined. Another example is the reduction in hemagglutinin contents. We have the specific affinity steps, which is also documented through robust test study and full-scale validation. Likewise, the validation of the clearance step justifies the removal of the hemagglutinins testing from routine in-process testing. But considering the European pharmacopoeia, we have maintained the routine testing in the final product. So, to conclude on the product, we have, through this QBD approach, obtained the desired final product with a biological safety item. But it was the same for stability, with a product at this time which is stable for more than 2 years at ambient temperature. So it was the same for tolerance, some of the tolerance item, which is based on different process steps. The last one would be related to efficacy, with an enrichment factor which varies from 10 to 21, and which is important to demonstrate that we recover the initial activity we have in the starting material. So at the end, all these items obtained through the QBD approach make that final product is an agreement with a defined quality target product profile, making this 10% IVIG in liquid form is stable, efficient, and safe. In conclusion, I will say that the QBD approach, by integrating robust test studies to a risk analysis process and also time and resources consuming, has generated very positive outputs. First, a strong rationale for process validation design and justification for process and product specification, and globally, an enhanced process and product knowledge and an improved process control strategy with justified critical process parameters and process character and their limits to obtain the final product characteristic we have designed. So for me, the key lessons of this approach are the final product is in full agreement with the design product, and the well-controlled process is the key for a compliant product obtained during routine manufacturing. And I will close with acknowledgement for all these teams that work on this project development, for process development team, for industrial and validation development teams, and mainly for the huge work they do for this approach, analytical development and control teams. Thank you.